In this video, we showcase how CoppeliaSim can be controlled via Python in various ways. In the first example, we demonstrate using an external Python script. We launch CoppeliaSim as usual, and a separate Python interpreter, which can be in the same machine, like in this case, or in another machine connected via TCP/IP. This method makes use of a communication client based on 0MQ. Once the Python package has been imported, we instantiate a client, which by default it connects to the same machine, and use the require method to access the desired remote object, in this case sim, which provides access to the core CoppeliaSim API functions. Now we load a scene, obtain the robot's handle, display its alias, and then retrieve the robot's associated functions. We initiate the simulation, modify the robot's maximum velocity using the retrieved functions, and then halt the simulation. The next example demonstrates a remote API client controlling 3 robots simultaneously. We launch 3 threads from a single client, each dedicated to a robot. The blue and red robots receive commands in joint space via a designated motion profile. The green robot uses inverse kinematics. Moreover, the remote API offers a stepping mode, enabling the external triggering of individual simulation phases. It efficiently supports function reentrancy and callback systems. Next, we'll illustrate the process of streaming and displaying an image from a vision sensor. The second approach to interfacing with CoppeliaSim using Python involves the Python client managing the CoppeliaSim library. This requires launching CoppeliaSim a bit differently. For instance, our Python script here loads the CoppeliaSim library, initiates a specific simulation scene, runs the simulation for 1000 steps, unloads the CoppeliaSim library, and concludes. The third method involves directly running Python from within CoppeliaSim. Notably, the interactive console offers dual versions, Python and Lua, that you can switch between any time. In our demonstration, a scene is initiated via command line, though GUI loading is equally feasible. This scene presents 3 cuboids, each steered by an embedded Python script. While these scripts can fulfill various roles, they primarily guide the cuboids along the y-axis in our scene. The first script operates without threading. The subsequent scripts, however, are threaded, with the second one being synchronized with the simulation loop. This ensures it operates in stepping mode, activating each simulation phase via the step command.